Okay, so guys, what I would like to do to start off today is to review a bit with you. We've already started this chapter, and the primary thing that we were talking about is what is a buffer system. Now, if you need to go back and look at your notes, please do, but let's review that there are two types of buffer systems. Type number one includes a weak acid, and what is the other component that needs to be there? It's conjugate base, which is usually coming from a salt of some kind. The other type of buffer system, we've got a weak base, and then what's the other required component? It's conjugate acid. Okay? Now, what's the purpose of a buffer? What are they good for? Why do we care? They resist changes in pH. Whatever the pH of the environment is, they will keep the pH nice and steady. And the last thing that we did, last class, if you go back and look, was we had buffer systems and we started adding things to it, like a strong acid or a strong base. And we didn't do any math with it, but we worked on how do you write the reaction that occurs. And that's what I want to start off with today. And I'll do the first one with you to review that thought process. So let's read through number one. It says, write the reaction that occurs when NaOH. Stop there. What is that? What kind of a base? Okay, a strong base is added to the following buffer system. Now they're already telling you it's a buffer system. They might not do that on a test question, but here's an acid, strong or weak? Weak. Buffers include weak acids, and then what is this? Sodium nitrite, what is that? It's a salt that contains nitrous acid's conjugate base. Okay. Before we can write out the reaction, what do you suggest I do first? Major species, sounds great. Okay, what do we always have in our list? Water. Okay. Oops. Okay. How do I deal with this compound right here? Should I write it together, split apart? Why split up? It's a strong base. Very good. Strong things dissociate. Okay. How do I deal with nitrous acid? What should I do? Why keep it together? It's a weak acid. Weak things do not dissociate much, so I'm going to write it together. And last compound, what should I do? Why separate it? It's a salt. Salts ionize. Okay. Do you remember what we're looking for? Like what kind of a reaction? Okay, a neutralization. What does neutralization mean? Acid plus base. Okay, well, guys, what in this list, what are my candidates for things that could even be an acid? Okay, water and nitrous acid. Okay. How do you know which one to pick? You pick the stronger acid, or let me say it to you another way, you pick the one that is more acidic. So what do you guys think? Water or nitrous acid? Which one is more acidic? Nitrous acid. Okay, and acid is always more acidic than water. Okay, so nitrous acid, acid plus, what base should I pick? Why OH? Good, I just wanted to hear you say it. OH because it is the king daddy, the strongest of the strong bases. Okay. Tell me my products. NO2 minus. And what else? Very good. Okay. Very nice. You guys do the second one. Same process. Yes, that was it. Okay. So there's the guys, there's the answer, but let's talk it out. Okay? So were you all okay with this list? Like, was just listing out the species, was that okay? All right. The part that becomes tricky is choosing, you know, what is going to be your acid, what's going to be your base. So in the list, we start with acid. Does any one of those things jump out at you? And why are we definitely choosing that one? It's the king daddy of acids, okay? So that's the easy part, okay? Acid plus, okay? But even if that weren't there, guys, remember, your choices for what could be acids go back to simple definitions. An acid is something that can give away a hydrogen. This can give away a hydrogen. So can this. So can this. Now this can't, because guys, at this point, we've worked with ammonia enough times that I would expect you to know, without being told, that ammonia is a weak base. It is not an acid. Just because it has hydrogen does not make it an acid. Okay. We chose this one though because it's the king daddy. Now the base, choosing the base is the more difficult part. Go back to simple definitions. Bases are things that can accept a hydrogen ion. That would be H2O, Cl minus, and ammonia. All right? Those are my three options. Now, somebody tell me, why can I immediately eliminate Cl minus? Okay. Because think about what that would form. Put Cl minus in this position right here. It would form what compound? HCl. Why is that not going to happen? It's a strong acid. Strong things don't form. Okay. So that's off the list. And then it's down between these two. Okay. Now I try to keep it simple by just saying which one of these is more basic. Well, again, guys, I would expect you to know at this point, ammonia is a weak base. It's going to be more basic than water. Okay? But even if you didn't know that, think about what the reaction would look like if you chose water. It would look like this. Okay? Do you remember last class what we said about hydronium? Is hydronium a strong acid? No. Is it a weak acid? No. It's on the borderline. Okay? This is a weak acid. Okay? Sort of medium acid, weaker acid. Which one is more likely to form? The weaker one. Because remember, weak means likes to go together. Okay? So if you're not sure which thing to pick, try some trial and error and see what comes out. Okay? Usually you can figure it out once you write out a couple of equations and see which one is more likely to happen. But we're going to get more practice with this as we go on. Okay. Now, we talked last class about what buffers are good for. And you told me at the start of class today, they're good for maintaining a constant pH without much fluctuation. And we talked about how lucky it is that we have buffers in our body that maintain the pH of our bloodstream and other aqueous environments. But buffers are not all powerful. I said if you go back in the chemical storeroom and start chugging hydrochloric acid, you will overpower your buffers. Buffers have limits. There's actually a term for it. Every buffer has what's called a buffering capacity. Okay? Which is simply this. It's how much, and notice these two species, the king daddies, how much strong acid or strong base can this buffer absorb without changing the pH? How much can it take before the pH starts to change? Now, what determines a buffer's buffering capacity has to do with the equation that I showed you last class. So take your equation sheets out if they're not out already. And I want you to look at this equation. Remember, I call it the Hendy-Haas. It's the second to last equation in this section. Look at the end of that reaction, or excuse me, that equation, where you see this. Okay, base over acid. What determines how much a buffer can absorb is the magnitude of these values. Now guys, let's refresh our memories. What do brackets mean? Molarity, concentration. How concentrated these parts of your buffer are is what determines the buffering capacity. Okay? And I'm gonna show this to you. Okay? I'll say those statements again if you didn't get a chance to write them down. Okay? Don't try to read everything all at once. Let's just take this piece by piece. It says, calculate the pH of each buffer system below. What am I trying to say with this right here? Acetic acid, okay? 5 molar acetic acid and 5 molar sodium acetate. That's a buffer. Guys, how do you find the pH of a buffer system? How do you do that? You use Hendy-Haas. Okay, let's do that. You have it right in front of you. It says pH equals pKa. Now what is that? What does pKa mean? Okay. The negative log of your Ka. Remember, if you forget that, it's written right below. Okay. They give us the Ka right here. Oops. 1.8 times 10 to the negative fifth plus the log of base over acid. Be careful how you answer this. Focus right here. What is the base in this buffer system? I'm not asking for the number. What entity is the base in this buffer system? Yeah, the acetate ion. Where is it coming from? It's coming from the salt. So there is its molarity. 5 molar. Base over acid. Well, here's my acid. That's the easy part. What's 5 divided by 5? What's the log of 1? 0. Please put this in your calculator, ladies and gentlemen. Tell me what you get. What is that pH? What do you got? 4.74? Okay. And that pH makes sense. This is an acidic buffer system. Should be below 7. Okay. Look at the second bullet here. Same acid, same salt, that means the same Ka value. What's different are the concentrations, okay? What's the pH of that one going to be? Why the same number? Yeah, because 0.05 divided by 0.05 is 1, the log of 1 is 0. We're going to get the same number. Okay, fine. Now let's read this statement. It says, after hydrochloric acid, which in its pure form is gaseous, in the gaseous state, is added to each buffer system, the first one has a resulting pH of 4.74. That means the pH did not budge. It stayed at 4.74. That's a buffer doing a good job. But the second buffer has a resulting pH of 4.56. Adding HCl caused the pH to drop a little bit. Which buffer has the better buffering capacity? What's our answer? The first one. And why is that? I mean, look at those two bullets. They're the same buffers. What's making the difference? The molarities. Remember what it said on the previous slide. Buffering capacity is a direct result of the magnitude of the molarities of its contents. The greater the molarities are within a buffer, the better its buffering capacity will be. Okay? It's like, adding an acid is like punching somebody in the stomach. It's like this buffer has better muscle tone than this one. Are you ready for the terrible pun? Are you ready? This buffer is buffer than this buffer. Wah, wah. No, that doesn't even deserve a bell. That was terrible. Okay? Now, guys, I would never give you just one single buffer system and say, does this buffer system have a good capacity? No, I would ask you to compare them and say which one is better. The one with the higher molarities will be better. Okay. All right. What else could you be asked with buffers? Well, you might be asked, and this could be in multiple choice or free response, ladies and gentlemen. You could be asked, which of the following buffer systems is the best choice? Okay, so let's say, let me give you a hypothetical situation. Let me pull this up. Okay, you are a lab assistant, okay, and your boss comes to you and says, you need to make a buffer system that's going to hold the pH steady at a pH of 9. That's your job, your task. You have to put together a buffer system that's going to hold the pH steady at 9.0. And very kindly, your boss doesn't just let you, doesn't just throw you to the wolves. Your boss gives you 3 choices, buffers A, B, and C. And for each, let's say, for each buffer system, you are given a Ka value for whatever the acid is in that buffer system. Here is how you're going to make your choice. I'm going to say something to you. I'll say it twice. When you are asked to choose a buffer system for some desired pH, in this case, 9.0, you want to choose the buffer system whose pKa, whose pKa is closest to your desired pH. Let me say that one more time. If you are given some desired pH and you're supposed to choose a buffer system, you want to choose the one whose pKa is closest to that desired pH. Now don't pick up your calculators. Put them down. Put them down. Okay? Tell me, how do you get from a Ka to a pKa again? Negative log. Okay, let's say this is in multiple choice. You don't have a calculator. We have talked about how to estimate this. Let's go over that again. If you take the negative log of some number in scientific notation, do you remember where is your answer going to come out to be? It's going to be somewhere close to that number. It might not be exactly 2.0, but it's going to be close. Do you remember that if this, tell me this first of all. What if this was 1.0 times 10 to the negative 2? What would my answer be here? 2.0, okay? But this is a higher number. Do you remember what that means? That this should be 1 point something. It'll be less than that number. So 1 point something. Where is this pKa going to fall? 12 point something. All right, how about the third one? 8 point something. Okay, just based on those estimates, which one do you think I'm going to choose? You got it. Okay, so if this is multiple choice and you don't have a calculator and you're answering a question like this, focus on your exponents. Now, let's go over this just one more time. I want to make sure that you're a good estimator. If this was 1.0 times 10 to the negative ninth, what would this be? 9. Well, this is just 1.3. That's just a little bit above 1.0, so this is going to be just a little bit below 9, which is good because I want a pH of 9. Okay. What if you were given an option like this? A fourth choice. And they might do that. So you could at least narrow it down to between C and D. Keep in mind, this one is going to give you an answer just slightly below 9. This is going to give you an answer greatly below 9, almost all the way to 8.0. This is the better choice. Okay? If this was in free response, then you do have your calculator. Don't just give estimates. Show me actual numbers. And then I would probably make a statement. Buffer C has a pKa closest to my desired pH. That's what I would say. Okay, ladies and gentlemen, we are going to change gears a little bit here. Okay, everything we just talked about is right there. We are moving to the land of titration. Do you guys remember what that word means? If you go into the lab and you do a titration, you're adding something to something. Not water. Acid plus base, okay? You're doing an acid-base reaction, okay? And we're going to see a lot of graphs in this section, all right? For example, this graph, here's the situation. You would have a set amount of acid. Okay, the amount of acid you have is not changing. And what are you adding to that acid? You are adding progressively more and more base. Now guys, if you're adding more and more base to something, what should happen to the pH? It should go up. And it does. But it doesn't go up in a linear fashion. It goes up like this. Okay? You start adding base, and the pH, yes, it does go up, but it creeps up. Ooh, hello. Hello. Okay. You're adding base, and the pH does go up, but it just creeps up slowly, and then all of a sudden, out of nowhere, seemingly, the pH shoots up like crazy, and then it slows down. Okay. We are going to eventually do a titration. That'll be our next lab, which is, I have no idea when. Okay. And this is the area where people get really frustrated. Okay. Guys, we are a society, humans are people that like instant gratification. And when you are doing a titration, you're adding base and you're adding base and you're adding more base and you're adding more base and you're monitoring that pH. And yeah, it's going up, but it's creeping up. And this is where there's always some lab group. Somebody puts their hand up and they're like, Miss G, mine's broken. Our titration is broken. It's not working. I mean, yeah, the pH is going up, but it's taking forever. And I say to you, be calm, my children. Okay? Patience is a virtue. And then here's what's happening. Okay, this is what happens next, because this always happens. Then I walk away, and as soon as I'm out of earshot, you're like, you know what, this is getting really boring. Just dump in a whole bunch of base. She'll never know. Yeah, she will. Okay? Yeah, she will know. Because here's what's going to happen. You're going to just start adding tons and tons of base, which is going to cause you to skip completely over that part of the graph. This area in here is a really sensitive area, meaning you're adding base and like adding a single drop of base. Maybe not even a drop, like a droplet. All right? Adding a single little droplet of base is going to cause your pH to shoot up by 4 units. Okay? You have to be patient and very careful, especially in this area. Don't get lazy. Let's talk about what this term equivalence point means. This is the formal definition. I'm going to give you a simpler one. Okay? Enough titrant, in this case the titrant would be a base, has been added to react exactly with the solution being analyzed, in this case the acid. Here's a simplified definition. Moles of acid equal moles of base. Okay? Equivalence, equal. Moles of acid equal moles of base. And you will notice, guys, on this graph, the equivalence point falls at a pH of 7. Great question. Will it always be at 7? No, it won't. However, if you are doing a titration between, write this down, a strong acid and a strong base, so a strong titration, the pH at equivalence will be 7. Strong acid plus strong base, the pH will be 7 at equivalence. When you start bringing in something weak into the mix, it will not be at 7. We're not going to get into that today, but we will next class. Okay? So, let's see what a titration and the calculations associated, what that looks like. Now, do you guys remember what those 3 letters stand for? Water, molarities, X's, okay? All of the problems we did in chapter 16 were what I call Womack's problems. Water was a reactant. Our ice tables included molarities. We were adding and subtracting X. I am giving you a new memory trick today. The types of problems we're going to be seeing today I call them Neumann Problems. And here's what those letters stand for. We're not going to be dealing with reactions with water as a reactant anymore. We will have reactions that are, if I can spell this correctly, neutralization reactions. What does that mean? Acid plus base. We will do ice tables, however, they won't have molarities in them. They will have numbers of moles in them. And we will not be adding and subtracting X anymore. We will be adding and subtracting actual numbers, which is good news for you, ladies and gentlemen, because that means no graphing. There's no unknown to solve for. There's no X. Right? Let's look at what these problems look like. Here it is. It says, titration of 40 mils of 0.2 molar, what acid is this, ladies and gentlemen? Perchloric, strong or weak? Okay. With, meaning this is the thing we have a set amount of. We have a set amount of acid. We're going to be adding to it 0.1 molar, what is this? Strong base, good. Calculate the pH after the following volumes of base have been added. 0. Okay, now hold on. It doesn't mean we have nothing. It means we have no base yet. So what do we have? Just the acid. Okay, well, let's be good little AP Chem students and let's list out our major species before we've added any base at all. What do I have in my list? What do I always have? Okay, what else? H plus? What else? Why'd you split those up? Because it's strong. Okay. Well, how do you find the pH of just a strong acid and nothing else? Do I need an ice table? No. Focus right here. Negative log of 0.2. Done. All right. Let me get to a fresh screen here. Okay. So, pH equals negative log of 0.2. Somebody put that in your calculator. Give me 3 decimal places. What do you got? All right. That's a pretty low pH. Does that make sense? I mean, think about it. What is the one thing that we have here? Strong acid. Yeah, that should be low. Okay. All right. First part done. Now, we start adding some base. And it said we're going to add 10 milliliters. Remember what the base was? It was KOH. Let's update our major species list. What should I add to the list now? K plus? How come you separated them? Okay. What is my reaction going to be? Okay. H plus what? Why'd you pick those two? I just wanted to make you say it. It tickles me. All right, what's my product here? Water. Okay. Did you all notice water is not one of my reactants? Do you agree? This is not a Womix. It's a Neumann. Which means, yes, I need an ice table, but it's a much simpler ice table. What do you guys think? Do we care about water? We still don't. Water is the social pariah of acid base, okay? In a Neumann, what type of numbers go in the table? Moles. Okay, let me come back to the problem. H plus was my first column. Guys, where is H plus coming from? What compound? Okay. I've got a molarity, but that's not what I want. I need number of moles. Aha. Okay. You have to change it to liters first, right? Okay. So 0.04 times 0.2, tell me what that is. Okay, she says it's this. 0.008 moles. Ladies and gentlemen, if you would like to write that into your Neumann ice table, go for it. But I'm going to write something else, and you can either do this with me, or you don't have to. It is totally what makes you feel happier. I am not going to write 0.008 moles. I don't like the dot. I don't like the zeros. It annoys me. Here's what I'm going to write. 8 millimoles. I did not say minimoles, just so we're clear. Millimoles. It's a prefix, milli. Now guys, why do I like millimoles better than moles? Here's why. I don't have to change into liters. Guys, most of these problems, your volumes are going to be given to you in milliliters. If you keep it in milliliters, 40 times 0.2, that gives me the number 8. I like the number 8 better than 0.008, but that's just me. Okay? Let's deal with this guy. OH minus, where is it coming from? What compound? Okay? Here's the molarity. Here's the volume. Tell me, somebody tell me, either number of moles or millimoles, your choice. Give me a number though. What is it? So either 0.001 moles or 1 millimole. Okay? Neumann ice tables, guys, I'm not going to say minus x. We're not dealing with x's. What will I be subtracting here? Actual numbers. Now, what number? Well, here's how you know. This reactant that I have circled is my limiting reactant. How did I know that just by looking at this? Yeah. It's the one that has less moles, and it's in, these are things in a 1-to-1 ratio. Guys, tell me one more time. Or, not one more time, but tell me from Chem 1, what does being a limiting reactant mean? The reactant that is completely used up first. Anybody want to guess what number I'm going to subtract here? You got it. Because look at what I have for OH. The reactant that is completely used up at the end. The numbers support the theory. Okay. Now we're not quite done yet. Yes?
It doesn't support
Wait, what do you mean? Yes. Let me cheat it wrong. Okay. Guys, keep coming back to what are we supposed to be solving for? A pH. What do you need to find a pH? Molarity of what? H plus? Okay, fine. Well, that's not a molarity. How do you change moles or millimoles, either one, into a molarity? What would you do? Divide by volume. Okay, hold on. You're right. The question is, what volume? We are at the end of this reaction where the acid and the base have been poured together into one container. Total volume. We had 40 milliliters of the acid, 10 of the base. Now guys, this is another reason why I like millimoles. Millimoles divided by milliliters equals regular old molarity. I like that. I don't have to convert anything to anything. How do I get the pH now? Negative log of this number? Okay, great. Give me the answer to 3 decimal places, please. 854. Okay. Okay. Look at our progress. Look at where we started. Look at where it is now. Why is it going up? We're adding base. It should be going up. Now, remember, we're in here, guys. Should it be going up by a lot? No, it's going to be creeping up. Okay. Let's come back. We've done this one. We've done this one. Now, this is, you think this is going to take forever. It's actually not. Because working with a different volume of base. Guys, is my reaction going to be any different than it was in the previous step? Same reaction. You know what else will be the same? The amount of acid. That's not going to change. The only thing that will be different will be this number right here. I want you to try the next step on your own. Do you want me to put the original question back up so you can have the numbers? Okay. 40 mils. You do that one on your own. Did you get that? Okay, so guys, let's think of the progress that we've done. Let me go back to the first two parts. 0.700, 0.854, 1.301. It's going up, right? Is it going up a lot? No, but that's okay because we're down in this area where it shouldn't be increasing by a lot. Okay? Please make a note. Listen. This particular step has a name. It's called the halfway point. This particular step, anybody want to guess where we are halfway to? Equivalence. So sometimes you'll see it called the halfway point. Sometimes it's called the half equivalence point. Okay? Now, why is it called that? Watch. This is the amount of acid that I had. This was the one. Listen, everybody. This was the one. Acid was the thing I had a set amount of. Okay? That's not changing. Do you all agree that the amount of acid has been cut in half? Do you agree? Okay. That's why it's called the halfway point. The thing that you have a set amount of has been neutralized by half. Keep going. You're going to find a unique situation here. Keep going. Okay. Now, guys, I did not get this number just because I happen to know it. I didn't just pull this out of thin air. Look at this ice table. Look at the end. What do you have? You have no leftover acid, no leftover base. What's the only thing you have? Water. What's the pH of water? 7.000. Okay? And this is, make a note to yourself, what's it called? We're at the equivalence point. And what's the definition of the equivalence point? Not molarity.
Moles of acid equal.
Moles of acid equal moles of base. Okay? I am at the equivalence point. And guys, did you notice 40 milliliters got us to the halfway point? Double it. 80 got us to the equivalence. If we were on the graph, ladies and gentlemen, the equivalence point is always at the most vertical part of your graph. So like right there. This would be 80. Cut that in half. That's where your halfway point would be. 80, 40. If you are given data from a graph, ladies and gentlemen, if you are given one of these points, you can always find the other. Because if you know 40 gets you to halfway, then 80 must get you to equivalence. If you know 80 gets you to equivalence, then 40 must get you halfway. Okay? Do the last one. There's one little part of this last part that is a little bit different, but I think you can handle it. Okay, why did I say this last step had something that was a little different? Yeah, the limiting reactant changed. Okay, my limiting reactant wasn't OH minus anymore. This time it was the acid. Let me say that to you another way. At the end of this reaction, I have excess base instead of having excess acid. This pH makes sense because I have, again, excess leftover base. My pH would be somewhere up in here now. Okay? So you need to be aware when you're doing these calculations of where are you in these curves, because a couple of you have asked the question, would a test question look like this and have 5 separate calculations to do within one titration curve? No. They are going to focus in on just one of these. The hard part is they're not going to tell you where you are. You have to figure that out. Am I just before the halfway point? Am I in between? Am I at the equivalence? Am I beyond the equivalence? You'll have to figure that out. They're not going to tell you, and that can be challenging. Okay? If we had a titration problem, guys, where instead of adding more and more base, we were adding more and more acid, then my curve would just look like this. Okay? Just same shape, just moving down pH instead of going up. Okay? So, next class, what we will get into is how does this titration situation change when one of these things is weak and it's not strong. Things are going to start to get crazy. Okay, but I'm going to stop there for today.